Okay, let's start our session. So our first speaker is Toni Shiroka. The title is there, so please start.
Okay, thanks. So this is a talk which starts with a question and ends perhaps also with a question. We are looking for collaborations for people who can help us to understand some, let's say, non-usual results we found in a NEMATIC topological superconductor. Now, this is work would not be possible without the collaboration of all these people here, in particular Professor Nakajima from University of Central Florida in US, and Gianrico Lamura, my long-term collaborator on CNR-spin in Italy. Now, a very short overview of the talk. I go through a very quick introduction just to make sure we are on the same page. So what exactly we mean by topological NEMATIC superconductors. Then we see a special case, which is this one, which really puzzled us a lot. And we go through two types of measurement, transport and magnetometry, and mu-SR. Now, most of you, or some of you, might not be even familiar with what is this technique. This is very important because it's a bulk technique. So there are many techniques which are nice to study these kind of things like STM or ARPES, but they suffer from the problems of surface, like defects or pinning or other, or local scale too small, inhomogeneities and so on. This is a very good technique for this kind of studies I will show later. And then I spent quite some time in discussion because this is the most important part of the whole talk, basically. So we are going to address at least this question. Do we need another vortex lattice paradigm? And if so, with which we should replace it? This is the main point, okay? Now, first, very quick introduction. I start with this slide. It's not very nice, no pictures, but it's important. In almost more than 10 years ago, Fu and Berg started with a, let's say, came up with a criterion, what we should call topological superconductor. And they came up with two main things. One is odd parity pairing symmetry with a full superconducting gap. These are very important, both. And then the other is that the Fermi surface must enclose the odd number of time-reversalinvariant momenta, it's so-called TRIM. This is something trivial. You do the mapping of summary surfaces, see where the momenta lie. So it is not difficult. This other instead is more difficult. By the way, when you see odd parity, most of you will think immediately p-type, but this is not so, because here we are talking material with spin-orbit coupling. Spin is not anymore a good quantum number. We have pseudo-spin instead. So this is something which is not the standard p-type you have in mind. Let's put it like this. And then as a subclass of this, we might have sometimes so-called NEMATIC topological superconductors, which is something we have seen here. Only in the superconducting phase, you have the lowering of the symmetry of the electron fluid below the symmetry of the underlying crystal lattice. And this spontaneously broken rotation symmetry is the fingerprint of nematicity in this case. One of the most well-known cases was that of this material here, which you see, this material here is the bismuth selenide topological insulator, which when doped with copper becomes a superconductor. Now here, I'm not going into much detail, but just to tell you, this is the, let's say, the equivalence between the standard liquid crystal NEMATIC. We have a director and the, let's say, the couples, the Cooper pairs, which have polarized, so to say, Cooper pairs in the material. So this is the ordinary superconductor. This is the NEMATIC one. What is very nice here is that this is some temperature. In this case, I don't know, 0.3 K or something like that. But you change the field. In one case, above the critical field, so high field, you have no modulation at all. But when you go below, you have a modulation, as you see here. And this is important. It's not only modulated, but it's modulated with lower symmetry than the hexagonal lattice. Therefore, this is a good candidate for topological superconductor. Here, I'm not going into much detail what I said, but what is important is this is seen in bulk properties, very important. So one is CP, which you show here, and the other is AC2. So both of these have the same type of symmetry. Now, the question which comes after is, do we have similar materials and how they behave? Because with one material, you can say whatever you wish. But if you have more, you can talk about the class, so what they behave as a class. This is our next slide. We spotted this, it's called calcium stanide, so tin calcium, basically. It's a very promising candidate, but to claim it as a topological NEMATIC superconductor, we have to do the measurements. And then we did some characterization. I will show you more in detail. So it has nothing special, I mean, low Tc, but it's important because it's topology non-trivial semi-metal. It comes from this, tin is semi-metal, basically. And then it prevents, I will show, it has a time reversal symmetry, which is preserved, but it has the broken rotation symmetry. I will show you later. What is important for now is this thing here. It fulfills the second condition, because from the Haas-Van Alphen oscillation, we see that this material encloses an odd number of trims, okay? But the question is, does it fulfill also the first condition, which is this, does it show odd parity pairing And if so, is this also nematic or not? If it is nematic, how it behaves under applied magnetic field. So we are going now to address all these questions, okay? This is the stage for starting. So puzzling case of calcium stannite with transport and magnetometer results. I will not spend so much time on here, but just to show you the important thing is that it's extremely symmetric, very high symmetric point group, 48 symmetry. You see it from here, I mean, it's a cubic crystal. And then it shows almost linear resistance. When you go at very low temperatures, you see the superconducting transition. What is nice is very narrow. Narrow means this is a good quality crystal, single crystal. What is important also, this number here. It seems trivial, but this is below the Tc of tin. Pure tin is 3.7. So this is not dirty tin, just to tell you, okay? And this is also seen in the magnetometry results. Now we go to something more interesting. We do, let's say, magnetotransport measurements. Now, here, when we are in the normal state, you see nothing. So this is not nematic in normal state. But as soon as you cool down, you see you have a twofold symmetry. We have also, but you believe it's clear to see, you can see it also from the axial polar plot, let's say. What is important is that clearly you see for some directions you are superconducting, for others you are not. And this is indeed seen also here. So AC2 in one direction different from AC2 in the other direction. So we have broken the rotational symmetry of the electron fluid in the superconducting state. What is also important is that now here we don't have time to go in detail, but the curve here is not the usual multi-band stuff which has negative curvature. It is linear here. And more importantly, we can, at least these pseudospins behave. This is a p-type behavior. So it seems that it shows this exactly what we expect, this odd parity pairing. But we want more. So more means we go with a mu-SR result. Since most of you are not, or some of you might not be familiar, I have to tell you quickly what we mean with this. Muons are just heavy electrons or light protons. Basically, they are unstable and decay. Enter the sample, they are born polarized 100%, so they have all the same direction. In the sample, they persist under the internal field or under applied field. In one case, it's called zero field internal. It's sensitive to even tiny local fields because it has a huge magnetic moment, or gyromagnetic ratio, if you wish. Or in transverse applied field, it's very sensitive to field modulation, in this case, in the superconducting phase. What is very important, this is purely magnetic probe, no quadrupole moment, and this is very, very important. They are homogeneously sampling the whole field distribution in the bulk. This is crucial. And the other thing which is also important, we are talking about the nematicity of electron fluid, and they sit far from nuclei, so we are probing electronic environment. This is also crucial. Now, how it looks like when you do a transverse field mu-SR experiment in a superconductor. This is a picture familiar to most of you. This is the vortices, how they look like with a hexagonal symmetry. And if you project this, you have the probability density function of fields. So minimum here, you have maxima here, and you have saddle points which are here. Now, what is important is that when you apply, this is the, let's say, the real case. You apply the field in the normal state, you see nothing. All muons see the same field. They don't decay. There is no reason to decay. They are all in phase, same polarization, and they keep it in time. No decay. When you put, let's say, when you enter slightly the superconducting phase, you have large lambda. Lambda is infinite, but then it becomes a bit shorter, then you have some modulation. Therefore, this decays a bit. When you are deep inside the superconducting phase, this decays a lot. The shortest lambda 0, and this decays the most. Now, this is theory. This is instead the experiment. You see, it's one-to-one. There is no need to comment here. What is very important is that this sharp peak you see here, this is the background due to sample holder. This does not change any. You see, it's just very narrow and always at the same position. What is extremely important is this one here. By doing the FFT of the signal, we get P of Ni, which is just P of B. So just compare this figure here with this figure here. They are the same, basically. Okay? So just by measuring this, we know that this material behaves as what we expect it to be, just a flux line lattice of vortices. Okay? Now, let's see what we get in our case. This is now more, to do our experiment, since we expect nematicity, we have to come with some clever setup. This clever setup consists in gluing cubes of sample, small pieces of sample, with this way. So this is the 110 direction, the diagonal face, and this instead is the edge of the cube. So by applying the field in this direction, we are in the so-called B parallel configuration. By applying the field in the plane, we are orthogonal with this direction. This is what we call B orthogonal direction, okay? I'm not going to more in detail, but this is just to distinguish the two cases we have measured. And now we go and see what we find in the first case. So now we are applying the field parallel to this direction. Here you see short time scales, nothing happens. But even if you go in long time scales, nothing happens. This is a very long experiment, a lot of statistics, 9 microseconds, if a lot for muons, and basically it's very hard to distinguish who is who. So it seems as we are in the superconducting phase, but nothing happens. Or basically, this is a material which has a huge lambda, because huge lambda means no decay of the signal of mu-SR. They are all in phase and stay in phase. Now you go to the other direction. First thing you see immediately is that there is a difference. This is just to check, this is not the main point, but this is just to check the so-called shielding fraction. So it tells you this is a superconductor. We can give also some limit for the superconducting fraction. It's not 0 for sure, it's more than half. But what is important is to compare these two. Now, in the about superconducting phase, we are here, it does not decay, but here it decays. Very little, but still decays. So it's distinguished from the other case, and therefore we can call this a signature of nematic behavior. Now, let's go further. This is a very important one for the theory. When we do zero field mu-SR, we expect nothing to happen. And in fact, nothing happens. But if there were some development of ferromagnetic order, which is a signature of time reversal symmetry breaking, these two curves will differ. These are above and below Tc. But as you see, nothing changes. Therefore, we conclude from this experiment, which is nil result experiment, but still very important, we conclude that the absence of differences seems to tell us that this material preserves time reversal symmetry. I will show you that this is very important later on. Now, let's try to summarize what we did until now. So by applying field different direction, we find in one case tiny depolarization, in another case no depolarization. These two allow us to tell there is a breaking of rotational symmetry. This is a confirmation of what we already know from the other measurements. This is local, let's say, local probe confirmation. The other thing is what I just told you, the preserved time reversal symmetry. If you go more into numerical, let's say, details, this is also very important. This is the standard vortex-lattice model, and we can, this is the famous Ernst-Helmont-Brand formula, which connects what we measure sigma with what we want, lambda, decay, okay? And from this, we can find lambda delta 0. What is important here is this number here. This is huge. I show it also here. And the other important thing is that we have a low T saturation, which is a signature of absence of low excitation. So this is fully gapped superconductor. This is also very important. And finally, we have also this other important result that this M star is measured from the Husvan Alphen, and if you put this together with this formula, we can extract what is NS. And this NS is extremely small. So this is very dilute, very suspicious, let's say, superconductor. Now, all what I told you refers to this sample. We should now try to go to a discussion, put this thing more in, let's say, in, how I'm doing with time. So how much minutes I have? 5, 10 minutes, I don't know. Roughly. Yeah, you have until 12 more minutes. Okay, I tried to finish earlier, so we have time to discuss. Anyway, what I wanted to tell here is that what we found here looks already a bit unusual, anomalous, but it's not the case, because if you put these together with the other materials, which also have been studied by mu-SR, here we find these, let's say, huge numbers. So by the way, we know also from AC2 what is psi in this case, and we get a K kappa of 60 for this material. The other have also very high values. So what is unusual here are these numbers, to compare with the standard ones like niobium. Here, this A52, here we have 1,600, or these very, very large numbers. And also what is important is the difference, huge difference between the normal state electron density and the superconducting electron density. These are, here they are different, but not so much different. Here is extremely different. So they are really a different class. You can really touch by hand. Now the question is, what does it mean? So now we try to put together also with some theory. This is, let's say, a modeling of what we have until now. So by putting together all these experimental results, we can constrain our let's say, models. So not anything will fit. So already from knowing that we have broken the C4-fold, let's say, symmetry, we are left with much less states. So we are left only with 10 states. And we can, since there are not so many, we can even try to check them one by one. And this has been done. What is important is this column here. L means there are zeros in the gap line, you see here, line nodes, point nodes, or even F. F means full, but it's only one F. All the rest are different, which means this is one of the requirements I just have shown here. We need something which should be fully gapped, because this is what the experiment is telling us. And the other is the time reversal symmetry invariance, which I have shown you via zero field mu-SR experiments, which tells that this superconducting gap has no complex components. So basically, these are also the pictorial, how it looks like. Basically, only this, let's say, candidate is the good one. okay? And then we come up with this possible gap function. Now you come to the real, let's say, purpose of this talk. The real purpose is why they are different and what can we say about the vortices in these materials. So now I'm not going to bother you with those details. Basically, here we are saying that in all these cases, we have some preferred direction which behave different from the other direction. And also in our case, these directions will be different, but the crucial thing is that these, let's say, directions are such that they tell us that these materials are nematic topological superconductors. And I have tried to demonstrate this in both cases. And what is more important, they are all characterized by these unusually large lambda values, which is clearly not corresponding to the normal state carrier density. Therefore, it comes natural to ask, but do these materials obey the standard Abrikoso model with this single peak and with broad distribution? Yes or no? We are almost sure no. And the question is, are there other possibilities? Probably yes, and what? This is what we are going to see next. Now, I would like to attract your attention to this paper. It's 30 years old, but still relevant. Very, very nice paper. It's called Phenomenological Theory of Unconventional Superconductors. Still has some very valid ideas. What is very valid ideas? OP here means order parameter. So in standard cases, in conventional superconductors, we have one component. Everything is well known. Mixed phase is described just in terms of Abrikoso state. Two-dimensional hexagonal, everyone is happy, and we find this. I have shown you the example. We find exactly what we expect to find. And in this case, we can use Helmut Brandt's formula, which links, as I told already, lambda to psi, to sigma. This we measure, this we find. Everything clear. But now comes the, let's say, the important and interesting part. What happens when you have some unconventional superconductivity? And then this paper tells us clearly we are allowed to have multi-component order parameter, which means different types of vortices can coexist. I'm not a theorist. If you wish to read it, it's very, very nice. It shows you all the possibilities. So symmetry is lowered, therefore everything is allowed, basically. In this case, we can have also, let's say, each order parameter component can produce its own independent topological stable vortice. This is interesting. And they bring an example. I don't know if this applies to our case, but one can be coreless non-axial vortices. Everything is explained here. And now we come to the real, let's say, the last but most important slide. We have been digging around asking if someone has tried something, and indeed someone has tried. And this is a very nice paper. It's not had been published yet, but has very, very nice idea. This is by Egor Babayev and Thomas Wynyard in England, Egor Babayev in Sweden. And they have come up with the same question as us. There are many people who are finding crazy results. Do we make a sense out of them? And the answer is yes. Now let me try to explain, spend some time on this. Now, if you go, here we are comparing conventional with nematic superconductors with more or less similar condition, let's say, same field. I'm not going to explain what, these are low fields, basically. It's complicated, but it's easy. You apply a field, let's say, 1.5 times AC1 or something in the low part. Now, what happens here, you see, there are two crucial results here. First is, this is, let's say, the red curve here corresponds to the red curve here. This is huge, very much broader than here. So we already see that if we have nematic superconductor, we should expect a narrow field distribution. And this is exactly what we find, because narrow field distribution, remember, no decay. This is the crucial point. The other thing, this is also the fingerprint of this kind of material, is a double peak. Now we don't observe a double peak, because this requires single crystal of the highest quality, but we are working on it. Now, of course, you will ask, okay, that's nice, but I want more. More means why you have one single peak here and why you have two peaks. This is very easy to understand and very nice, because it has to do with fundamental symmetries. Here we have only one number which describes the vortex lines. It's kappa. Okay, it's the ratio of lambda and psi, but it's a number. Therefore, we have only one peak. Here instead we have two, because they describe there, let's say, we don't have any more vortices, but they say we have Skyrman, or even better, Skyrman stripes, especially at low fields. When you go to high field, this model then converges to the standard one, which means standard one is the standard vortices. There, it's hard to distinguish one case from the other, but at low fields, we can distinguish the two. And what is more important, where this double peak comes from? This is very easy to understand. Look here, we have let's say these are stripes. This is stripes of Skyrmans, but there is an inter-Skyrman distance. This is one length scale, and there is a stripe periodicity. This is another length scale. And when you put these together, it comes naturally, it's come obvious that you should have also two peaks, because you have two distributions, basically. So this is our, let's say, best knowledge or best effort to explain our crazy results. But of course, I'm open, and I will be willing to have also your feedback on this, let's say, issue. And what is important is that what we have shown here is for one case, but this applies to the whole class. So I expect this to have further developments later on when people start to study more seriously topological nematic superconductors. So this brings me to the last slide. So just to summarize, we have seen with mu-SR magnetotransport measurements on this material, on calcium stanide, that we have a broken rotational symmetry. Second, we have a preserved, from zero field mu-SR, preserved time reversal symmetry. Then I have shown you from the numerical, let's say, result that this is fully gapped. And we even tried to figure out what it is, and we have come up with this one. Of course, all this is still work in progress, but it should not be considered as a last word, but as a starting point for addressing all these very interesting and unconventional properties of the mixed state of nematic superconductors. So thanks for your attention. So I leave these, perhaps it might be.
Thank you very much. Remarkable. Questions?
So thanks for this interesting talk. The multi-gap superconductivity was considered to be a mathematical trick of no interest for about 1958, the Bardeen, and even after magnesium diboride, many people started to say that it was just a electron-phonon coupling. On the contrary, CaSn and myself, and we showed really that it's completely different physics from a single gap superconductivity. And Baba have shown since the early time, the fact that you have this kind of complex superconductivity. I think that your results are really, really compelling, really make a point.
I hope we open a new, let's say, a new field of study.
Because
people are more involved, more.
The people understood
willing
that
to study this.
When the BCS formula is wrong, so the correct formula is Bogoliubov form, and this was considered not interesting. So only in this meeting we had many other talks.
After some years, people realized that
it's completely different physics. That is important.
I thank you for your comments. Yes, it's very pertinent.
More questions? Please.
I expect some nasty questions from this guy.
So what sets the two length scales? So you have two kind of size.
You mean in this picture here? Sorry.
Yes.
Here?
Yes.
This case, this is a good question. They claim that this is very difficult, but they have done numerical simulation in, let's say, reasonable cases. And to answer your question, what sets is the applied field. So the higher the applied field, the more squeezed these become, until the two scales become just one, when you are very close.
But even if you do numerical simulations, you have to start with an Hamiltonian with two different numbers.
You can read this paper, it's very short. It's a PRL, basically, but they have also a long version. It's not yet published. It's still where it is here. So this paper, I can give you it's easy to, and they show exactly what they do. They take V1, V2, and then to cover the plane tessellation, and then start to put vortices and see these skirmins, let's say, and then start to see what you get. But this goes beyond my, let's say, field of expertise. But this is a short paper, easy to read, very clear. So it really addresses this problem. So the question in their paper, so the title of the paper is how muons, what is the muon stopping profile in a topological nematic superconductor? So exactly this question. But I don't know exactly. What I know after reading the paper is that basically the density of these skirmins and their periodicity depends essentially on the applied field. It might have to do also with some anisotropy of the material. But I don't know how exactly they try to model this. But as I said, this is still a very virgin ground, open field. We have more questions than answers. So I try to be honest, just showing what we get, and trying to attempt to answer questions. Our paper, by the way, stayed by referees for almost 1 year because they were always back and forth. When you try to publish something unknown or unusual, then you get this kind of reaction, let's say. It's not something, okay, everything known, next paper. No, we have to wait for a long time to repeat measurements, to grow another crystal to make sure this is exactly what we claim it to be. Anyway, thanks for the question.
Okay. Have a minute for comment? Short or not?
Time for the next talk.
Times the next talk, or maybe very quick. Okay, thank you for a beautiful talk. Just one brief comment. You remember the talk of Christina? And this is exactly sort of like
we already had some discussion with the chair about this thing, but he now have seen exactly the results. So.
Yeah.
Okay, we can discuss even later. Thanks.
Sure. Well, thank you very much again. And